Welcome to this explainer. Today we are tackling what is literally the ultimate bottleneck in AI scaling, and we're going to look at a truly radical mathematical framework that's been proposed to completely bypass it. If you follow high-dimensional machine learning, you know that the O(n)² constraint is a massive, unavoidable wall. Basically, every single time you double your data, your computation time quadruples. It's brutal. So today we're exploring a fascinating proposition. What if we transition away from flat, linear context windows entirely and move towards non-local geometric routing matrices by tapping into arithmetic group actions? So here's our roadmap for today. We'll quickly move through 1. Escaping the attention bottleneck. 2. The 4 pillars of escape. 3. The math of geometric routing. 4. Translating math into code. 5. Topological firewalls and stability. And finally wrap up with 6. A unified computation theory.
All right, let's jump right into part 1, escaping the attention bottleneck. Like we just mentioned, traditional linear context windows hit a massive wall with that O(n)² quadratic complexity. Every time you add a new token, the computational burden multiplies exponentially. There's just no getting around it. But utilizing a rather profound mathematical structure called the global Adel ring actually offers a real escape route. It allows us to shift away from those linear, flat sequences and move toward non-local geometric routing matrices. In this comparison brilliantly illustrates the stark contrast. We're basically moving from a dense, monolithic, quadratic system to a highly localized, factored approach using discrete parallel dimensions. Just look at that scaling complexity shift. The old monolithic architectures are completely replaced, so we can achieve optimized, localized retrieval using infinite dimensional group actions. It's a total paradigm shift.
Let's move on to part 2, the 4 pillars of escape.
To actually pull off this massive leap in efficiency, the new architecture fundamentally relies on 4 really profound mathematical concepts. Think of these as our core heroes driving the whole protocol. We have the global Adel ring acting as our radical space factorizer, Arthur's trace formula for instantaneous O(n) data retrieval, the Setteke isomorphism for geometric compression, and finally the Artin conductor, which acts as our non-abelian topological firewall.
Now, before we look at the raw equations, it's super important to understand that this global Adel ring acts as our primary structural shift. It instantly telescopes infinite dimensional representation spaces. What that means is it collapses massive, complex data into manageable, discrete points. So instead of searching through a dense, never-ending linear sequence, our data retrieval happens within a sparse, factored topological space. It's like finding exactly what you need in a giant library instantly, without checking every single book.
Okay, part 3, the math of geometric routing. This is where we get to the really good stuff. Looking right at the anatomy of this equation on screen, notice how the A physically splits the continuous macroscopic data sheaf, represented there by the R for real numbers, from the QP, which are the discrete parallel prime fields or p-adic dimensions. And you see that pi symbol? That represents the restricted product rule. It ensures that valid states only have fractional parts in a finite number of prime fields at once. This is exactly what creates that beautifully sparse topological space for our data retrieval.
Now check out the balance scale set up in this next equation. It maps the macroscopic data orbits on the left, the geometry, to the microscopic quantum distributions on the right, the spectrum. Here's the genius part. Any imbalance or informational discrepancy leaves a distinct algebraic fingerprint. This allows for O(n) retrieval. That means instant lookup, regardless of how massive your data size is, without any sequential step scanning. The formula just flags these discrepancies simultaneously across the entire spectrum.
So, the really crucial point here is how the Setteke isomorphism condenses these highly entangled, infinite dimensional matrices into a rigid algebraic lattice of complex scalar invariants. This severely minimizes the computational weight overhead. It literally lifts the transformations through that funnel shape you see here, condensing them right into the torus shape of the Langlands dual group. That is what gives us background control over these incredibly massive spaces. Let's see how this actually builds a neural network in practice. The single-dense quadratic matrix is broken down, decomposed, into parallel optimized arrays, all tracked safely by a subharmonic fractional while ratio clock. We've effectively shifted from strict, punishing quadratic limits to a tightly bounded, parallel system.
But you might be wondering, how do these separate subblocks actually stay coherent? Well, to keep these parallel lanes in perfect sync, look at the delta symbol there, the transfer factors. They act as a geometric feedback loop.
They instantly modulate weights across the tensor lanes without relying on explicit, computationally expensive pairwise dot products. Information in one single tensor lane seamlessly maps right back to the global group. And to protect all this delicate parallel synchronization from phase noise, Go's fundamental lemma steps in as this absolute purity shield. As the table lays out, it upgrades what would normally be statistical approximations into exact, rigid algebraic identities. The boundary interfaces are perfectly sealed into absolute global sync. Any fractional leakage across channels literally becomes zero.
Which naturally brings us to part 4, translating math into code. If you're sitting there wondering how on earth this abstract, non-abelian math actually runs on a physical GPU, just look right at this PyTorch code block. You can clearly see how the matrix Gaussian for decay and the determinate scale metric for nonlinear gating map directly into the executable tensor logic. It completely mirrors the Gillet-Soul torsion. This code physically maps the trace-driven oscillator directly into PyTorch, successfully capping phase noise in the forward pass, exactly the way the mathematical theory demands.
And checking out this next snippet, focus on the delta factors in the code. The endoscopic routing is physically executing that geometric feedback loop we talked about earlier. Local tensor states are natively modulating across contexts via these learned delta factors. The parallel activation lanes are explicitly routed using these geometric constraints, completely bypassing the need for those dense dot product matrices.
Furthermore, during the training process, the system uses Arthur's trace loss to constantly audit these transfer factors. By squaring the difference between the geometric trace and the spectral trace, this loss function mathematically kills interlane jitter. It prevents model collapse by enforcing the exact identity between the metric strain and the spectral representation. It is incredibly elegant.
All right, part 5, topological firewalls and stability.
So how does a system this vast and complex protect itself from total chaos or corruption during live processing? Well, when gradient backpressure spikes, pushing the conductor exponent into a critical danger zone, topological circuit breakers kick in. They ruthlessly overwrite the corrupted, localized lanes with pure zero tensors. This instantly isolates the noise before initiating a graded, seamless phase sweep recovery to restore global stability.
You can actually visually verify this stability when it's mapped onto a Poincare disk. It contrasts the beautiful, centralized equilibrium of a healthy state directly against the quarantined rogue links of an active firewall throttle. Notice how the rogue links are literally pushed out to the perimeter? It physically demonstrates exactly how the architecture prevents contagion from spreading across the network.
Finally, let's wrap this up with part 6, a unified computation theory.
Bringing all these structural changes and deep mathematical proofs together, we arrive at a truly profound vision for the future of processing power. This framework heavily suggests that high-dimensional AI can indeed scale infinitely without those hardware-crippling bottlenecks. We are looking at replacing dense, heavy compute with pure, instantaneous O((1) spectral data retrieval. Flat token indexing gives way to Adelic parallel dimensions, all secured at their very foundation by absolute mathematical purity.
Which leaves us with a massive, massive final question to ponder. If quadratic limits are completely inescapable in traditional models, is embracing this level of absolute mathematical purity the only viable path forward for the future of AI? It fundamentally challenges literally everything we currently accept about scaling. Thank you so much for joining this explainer. I really hope this provided a clear visual breakdown of how non-abelian mathematics might just rewrite the rules of computation entirely.